Okay, what questions do you guys have today? $24. Okay. So let's do the first part. When t equals 0, you get square root of 25, which is 5, times 9 is 45. 100 minus 45 is 55, so we'll put 55 in there. At 16, you get 25 minus 16, which is 9. Square root of 9 is 3. 3 times 9 is 27. 100 minus 27 is 73. And at 25, we've got 0, so just 100. Yeah. Now I have to find the room's average temperature, which is actually the hard part of this problem, right? Yeah. So what I want to do is I want to compute 1 over 25 minus 0, because that's where the end and the start are for the domain. 0 to 25. 100 minus 9 square roots of 25 minus t dt. So we need to find an antiderivative for this, basically. And we know how the power rule works. So we're going to look at this and we're going to see, okay, that's going to be 100t. I'm going to have minus 9 times probably some constant times, well, this is a square root. This is like t to the 1/2. So what's going to look like if I would have undone the 1/2 power, I would have had to start at a 3/2 power. Does that kind of make sense? So I'm going to be looking for something that looks like 25 minus t to the 3/2. I just have to figure out what that constant is. Okay. So we think it's going to be of this form, just because I know that if I take the derivative of this thing, I'm going to be ending up with a square root of 25 minus t. Okay. So we're going to look at that. We're going to take the derivative and make sure that whatever constant I put in there leaves me with just the 9 after I take the derivative. Okay, so minus 9c, 25 minus t to the 3/2. If I take the derivative of that, that's going to be minus 9c times 3/2 times 25 minus t to the 1/2 times minus 1 from the chain rule, right? Because I have to do the chain rule on that minus t bit. Okay, so I can solve for c because I want this whole thing to equal minus 9, 25 minus t to the 1/2. That's what I want it to equal because that's what I have up here, right? We thought it was going to look like this. We want it to equal this after I take the derivative of this thing, so I set these two equal. I can cancel the minus 9s, I can cancel that bit. I get that minus c times 3 halves equals 1. So c equals minus 2/3. Okay, so my antiderivative is $100t. I've got minus 2/3 of that, so this is going to be plus 6 times 25 minus t to the 3 halves. Let's just check. If I bring down the 3 halves, 6 turns into 9. The minus sign comes from that, so yeah, this looks like it's going to work out for me. Okay, so the integral then that we're trying to compute well, it's going to be 1 over 25 times 100t minus 6, 25 minus t to the 3 halves, evaluated at 0 and 25. Right. 1 over 25. I evaluate that at 25, 2,500, and that'll be 0. Okay, so 2,500 is the evaluation at 25 minus, if I evaluate at 0, this will be 0, and I'll get a minus 6 times the square root of 25 cubed is 125. So 1 over 25 times 2,500 minus 6 of those, well, 2 of those is 250, so 3 of the 2 of those is going to be 750. So 1 over 25 times 1750 is 70. It is, you're right. So that's going to be 3250. Which is slightly concerning. Because that's bigger than 100, and we can't have a bigger than 100. So where's my minus sign error? Do I have a minus sign error? Oh, that's a plus, isn't it? Yeah, this is a plus. So that's a plus. The 3250 wasn't going to work for me because 3250 divided by 25 is bigger than 100, and this function didn't get bigger than 100. So the average value is certainly not bigger than the maximum value. So 1750 again. So 70. Let's try that. Okay. Questions on that one? Yeah. This? That's a 0. It just didn't turn out very well. You can kind of see the middle of it there, but better. Other questions? 13? 19? I want the total area between the graph and the x-axis, and we've got this function minus x squared minus 3x equals f of x, and that's between -4 and 2. Okay, so let's factor this and see where the roots are. It looks like there was going to be a root at 0, and there's going to be a root at -3, because this thing factors as negative x plus 3 times x. We good with that? Okay. And so this is upside down. Oh, that's crappy. So we got a parabola that looks kind of like this. Let's put 2 over here because 2 shouldn't be as far away as 4 is. Okay. So sort of the problem with this one is I can't just take the regular integral. I have to break it into 3 pieces and take 3 integrals. Okay. So the first thing we had to do is we had to figure out where it switches from positive to negative with where those roots are. And then this area, so I'm taking the integral from -4 to 2 of the absolute value of f of x dx, because that flips up everything above the x-axis and you get a positive area on everything. But because the absolute value switches at 2 spots here, we're going to switch from -4 to -3. And I'm going to take the negative of this function because I want to make it the positive version. So that's going to be x squared plus 3x dx. And then I'm going to add to that the integral from -3 up until 0 of the function itself, because the function itself is on the top side of the axis. So that's minus x squared minus 3x. And then the last part is we have to add dx. And then we have to add the integral from 0 to 2 of the negative of the function again, so x squared plus 3x dx. So I have to do these three antiderivative integrals. Yeah. What's nice is I only have to find the antiderivative once because they're basically all the same, except for this one has a minus sign attached to it. Okay, so the antiderivative, maybe we'll do that in some scratch work somewhere here. So the antiderivative of x squared is x cubed over 3, because if I take the derivative of that, the 3 comes down, cancels, and I get the x squared, plus 3/2 x squared. For the 3x, if I take the derivative of this, I get the 3x. Okay. And I'm going to use a plus or a minus there because some of them are, this one's a +1, this one's a -1, this one's a +1. Okay, so what we've got is, got the +1, so x cubed over 3, plus 3x squared over 2, evaluated at -4 and -3. And we're going to add to that the negative of x cubed over 3 plus 3x squared over 2, evaluated at -3 and 0. And we're going to add to that the positive of x cubed over 3 plus 3x squared over 2. And this one's evaluated at 0 and 2. Okay, so let's do that. We plug in a -3, I get a 27 thirds. I plug in a -3, I get plus, sorry, that's 81 thirds. Nope, sorry, it's not. -27 halves. We're good. Okay, so there's the positive bit. The subtraction bit is the -4. So at -4, that becomes a -64 thirds and a plus 48 halves. Okay, then I'm going to subtract. At 0, I get 0. And then at -3, well, I've already done the -3 bit. It's this, right? And then we'll add in at 2, which is 8 thirds, plus 12 halves, minus 0. Okay. So I got those three things to add together. It looks like it's going to be easier to work with sixths, probably. Let's make this a 24. Let's make this a 6. Actually, we're going to end up working with thirds because this is a minus, which makes it a plus. So I've got 2 of these, and I'm going to cancel this one. So this is going to be minus 54 thirds plus 27 plus 64 thirds minus 24 plus 8 thirds plus 6. So that's 3. So I've got 9. And then there's 10 thirds, 18 thirds. 18 thirds is 6, so this is 6 plus 9 is 15. Hopefully all my arithmetic is correct, but I think we're down to 15. Okay. Questions on that one? Some of the arithmetic gets a little tough, but just have to work through it. Keep yourself organized. Other things you want to talk about today? Yeah. Yeah. Okay, so we're trying to find the derivative of this again. And the fundamental theorem of calculus says this is going to be equal to the inside function from the integral, because I'm differentiating an integral, so I shouldn't go anywhere. So I should still have the cosine function as part of this thing. But it's going to be applied at the variable part of the boundary. So that's the cosine of the sine inverse of x. But then the chain rule says I have to multiply by the derivative of the sine inverse of x, right? And that is 1 over the square root of 1 minus x squared. Okay. Okay, so the part that we want to look at is this. Okay, So I should be able to look at this sine inverse of x, and sine inverse of x, this is the angle which has a sine of x over 1. Good with that? Okay. So now I'm just going to draw the triangle that corresponds to that angle. So if this is sine inverse of x, this angle should have a sine of x over 1, which means the opposite side over the hypotenuse should be x over 1. And then I can fill in the rest of the triangle with just the Pythagorean theorem. So Pythagorean theorem says this side squared plus this side squared should equal this side squared. So this side squared minus this side squared should equal this side squared. So you get 1 minus x squared here. And now this is the cosine of this angle that we just drew. And the cosine of the angle we just drew is the adjacent side over the hypotenuse. So that's going to be equal to the square root of 1 minus x squared times, now here, 1 over square root 1 minus x squared. Cancel, I get 1. Yeah. Other questions? Yeah, the hard way to do these. Okay. So we want to take the derivative of the integral. We're going to go 0 to x to the 4th, e to the minus t dt. And it says first evaluate the integral and then differentiate the evaluation. Okay. The first thing we're going to do is we're going to evaluate the integral. We're going to ignore that we're going to take a derivative here. So if we want to do that, I need to find an antiderivative for this. So it's going to look like e to the minus t again with some constant multiplied by it. And the antiderivative in this case is going to be minus e to the minus t. Because if I take the derivative of that, I get e to the minus t again, but I have to multiply by a minus 1 because the chain rule up here and those minus signs would cancel. I just get e to the t. So I want to evaluate this at 0 and x to the 4th. So I will get minus e to the minus x to the 4th. Good. Okay. I don't know what this pair of boxes is for, but I'm going to put minus e to the minus 4th in there because that's where I'm going to put what I'm going to take the derivative of. So you go minus e where's my caret to the minus, I said x to the 4th, right? Yeah. Oh, Okay, it doesn't even want us to evaluate yet. I see what those things are supposed to be. We're just going to put the antiderivative in there. And then we're going to tell it that we're going to eventually evaluate the antiderivative at 0 and x to the 4. I think that's probably what it wants. Yeah, okay. You guys see what it was asking for there? So we found the antiderivative. We didn't actually evaluate it yet, but we just found the antiderivative, and we're going to eventually evaluate it at 0 and x to the 4. Okay, so this one has the minus sign. Is this the only one that has the minus sign? Yeah, this is the only one with the minus sign, so it's going to be that one, right? Oh, wait, what? Is there any difference between A and D? A and B have that minus sign difference. You're saying there's, what about A and D? Are there any differences there? The problem is I want either A or D because, oh no, I don't. Never mind. I didn't want B. Sorry. So A and D are no different. So that's maybe a hint that you don't want them, maybe. But okay, so if I differentiate this, well, if I evaluate it first, I get minus e to the minus x to the 4th, right? I think I do want A or D. Because if I take the derivative of this, what's going to happen is I'm going to have, so the derivative of minus e to the minus x to the 4th, that's going to be minus e to the minus x to the 4th times the derivative of minus x to the 4th. So these minus signs are going to cancel. I'm going to end up with a plus sign. I'm going to have an e to the x to the 4th times 4x cubed eventually. So I want it to end up positive. And so I need one of these two guys. Any idea which one I should pick? They were the same answer, right? That's so weird. But okay. I will send another email off to them about this stuff. Oh, and then simplify. Well, what did I say it was? E to the, Yeah, that's confusing and frustrating. Questions on that one? Just, I actually took the derivative. Or here, you've got e to the minus x to the minus fourth. Sorry, e to the minus x to the fourth times the derivative of x to the fourth. So that's all that is e to the x to the minus x to the fourth, and the derivative of x to the fourth is 4x cubed. So you can just take this and write it down there. Other questions? So the inside here expression is going to be as a t thing because it goes in to the integral, which has t as its variable. But the outside, after you've completed the integration, is going to be a function of x. So outside, you're going to be using x. Does that make sense? So right now, I'm going to use the product rule. I've got d dx of x integral 0x squared secant of t. Okay. So I've got a product of two functions of x. This is a function of x and this is a function of x, and I'm taking the derivative. So I get to use the product rule. It says take the first times the derivative of the second. And the derivative of the second, we can use the fundamental theorem of calculus. It's going to be the secant of t to the fourth, which is x to the squared to the fourth, times the chain rule part times 2x. Okay. Plus the first times, the derivative of the first times the second. So then that's 0 to x squared secant t to the fourth. So I've got 2x squared secant of x to the 8th plus the integral from 0 to x squared secant t to the fourth dt. And so that's what we're going to put in here. Oh, these are starting at 2. Doesn't matter. That's just the constant bit. And you take derivatives of constants, they don't change. So so this goes secant of t to the fourth. dt, and then here I've got 2x to the second secant of x to the 8th. Okay. Questions on that one? Okay. We see why it's using t's and x's now. Yeah. It's a little weird when it asks you to do that, but yeah. Because it's a product rule, that's what you get. Yeah. Other questions we have on this stuff? 22? Okay. Okay, I'm gonna pick I'm gonna pick this one. I was a little confused, but the 2's inside the integral there. I don't want the 2 inside the integral. Okay, so the reason here, when I plug in x equals 8, I want to get 2 out. Are we good with that? Okay, so if I change the top bound to 8, from 8 to 8, I don't do anything. So the area from 8 to 8 of the tangent function is going to be 0. But I want the entire function to be equal to 2, so I add the 2 at the end. So if I plug 8 into this, I get an area of 0, and then I add 2 to it, so that y is equal to 2 when x is equal to 8. Okay. And then the derivative is just fine, right? Because if I take the derivative of this, the derivative of the 2 is 0. The derivative of this by the fundamental theorem of calculus is just the tangent evaluated at x, which is the tangent of x, so that's good. On this one, which I was slightly tempted to at first, but the derivative here is the tangent of x plus 2, because that's the entire thing that's inside the integral, and I don't want the derivative to have that plus 2 on it. Plus, if I put in 8 here, I get 0 out, because this is still the thing that I'm taking the area under. I get 0, but I don't have an added 2 to it. So that one's wrong. This one, when I put an 8 up here, I'm finding an area between 2 and 2 and 8 of this stuff, which is very likely positive or negative. The tangent's positive and negative, but it's probably not going to be equal to 2. And the derivative's not going to be just the tangent of x either. It's going to be the tangent of x plus 8. So this one doesn't have the right derivative. This one would have the right derivative, but when I plug in 8, I am very likely not going to get 2 out, because the integral from 2 to 8 of the tangent is probably not negative 6. Okay. So I'm going to pick that one. Okay. This can be proven using the fundamental theorem of calculus. The integral is a solution because this integral is equal to 0. Oh, well, equal to y prime. And the constant outside of the integral is equal to y of 2. And the lower bound of the integral is equal to 8. Yeah, that's not really the reasoning, but those are true statements. So, well, what? Oh, sorry, y of 8. Y of 8 is supposed to be equal to 2. There we go. Okay. Now they're definitely true statements. Okay. Good on that one? Other things you guys want to talk about today? Some of this stuff's a little tricky, but the concepts are really important for future stuff. Anybody online have some questions? Okay, I'm going to talk a little bit about substitution to get us started on that. Let's set up a new page. Does anybody use this OneNote notebook that I linked to you guys early on to look at class notes at all, or not? No, just, well, if you want to follow along while you watch the videos, that's fine too. But like, does anybody just open this up and scroll through it? No. Okay. Just wondered. Okay, so substitution. This is undoing the chain rule. Okay, so let's look at an integral where I'd have to use substitution. So so if I had minus e to the minus t, I know that that's what this antiderivative is, plus c, right? So if I was going to take the derivative of this, what I would get would be minus e to the minus t again, times the derivative of minus t, and then plus 0 because the derivative of c is 0, right? But this is the chain rule bit, yeah, where you multiply by the derivative of the inside function. Okay. So this is just e to the minus t, because this bit's equal to minus 1, right? Okay, so I have to figure out how to undo that somehow. And what'd be nice is if inside this integral, I could split it up and I could find this part of it inside the integral. Okay, so I know that this bit up here looks like it wants to be part of an inside function. And so I'm going to try and figure out where that chain rule happened. And sometimes I might have to fit it in, or sometimes I have to do some algebra to fit it in. But I'm gonna think about this thing as the inside function. And I want to get this to look like e to the, put it there, and then I'm going to have the derivative of that inside function. And I'm going to have a dt here, but I also have to divide off by that in some sense in this case. So there's like this minus 1 here, right, that's floating around. And this might not be the best way to do the general case, but this works pretty well for this case. And so I've got this extra minus 1 that I want to float around in here. So I have to multiply and divide by that minus 1 at the same time so that I can kind of fit it in. So one of them is going to come outside the integral. And then one of them stays inside. Leave this one inside. And then the whole thing then becomes the minus this. And this is the exact antiderivative for e to the minus t. So minus e to the minus t. And we have to add c at the end because it's an integral. Okay. That was kind of weird, but that's the general process for how this stuff works. So let's maybe do one where I can't actually sort of do this multiply divide thing, and maybe I have some other sort of technique that I have to use. So let's look at the integral from, say, indefinite integral from 3x squared minus 7 cubed times 6x dx. Okay, so what's nice about this one? This looks like an inside function again. Maybe that green's hard to see. Yellow looks better. So I've got this inside function, and the derivative of the inside function shows up right there, which is nice. Okay. So I'm going to treat this a little bit like how we did chain rule stuff, where I'm going to actually explicitly say that g of x equals 3x squared plus minus 7. So dg dx, I'm going to write it with the dg dx because it makes things easier for me. And I'm actually going to write it in differential form rather than dg dx form. So dg equals 6x dx if I write it in differential form. Instead of dg dx, you keep the dx on the other side. And now we're going to use these two equations to substitute in here. So this equation goes in right here. And orange. This equation we're going to replace over here. So we decided what the inside function was. We get two equations using the inside function, and then I get the integral g cubed dg. We're all good with that? And I can find the antiderivative of g cubed pretty easily. That's g to the 4th over 4 plus a constant. But my original expression was in x's, so now I have to substitute back to get 3x squared minus 7 to the 4th over 4 plus a constant. And that's now my antiderivative. If I would use the chain rule on this, the 4's would cancel. I'd multiply by a 6x at the end, and I would get this thing as the derivative of this. This substitution technique allows me to kind of keep track of which part was the derivative of the inside bit and which part was the derivative of the outside bit. Okay. So let's try a couple more of those. Let's look at, say, the integral from nothing to nothing, indefinite integral. Let's look at 2x squared minus x plus 1 to the 4th. And then let's go 8x minus 2 dx. So what looks like it should be my inside function? Yeah, this looks like it should be my inside function. So we're going to call that g of x. And then dg will equal 4x minus 1 dx. So far, so good? Okay. I don't have 4x minus 1 dx exactly over here. I've got sort of twice that. But let's do something here. I'm going to solve for dx to get dx by itself. This is going to tell me that dx is equal to dg over 4x minus 1. Okay. And I will use that expression to substitute in, and I will use this expression to substitute in. So this is going to equal the integral of g to the 4th times 8x minus 2 times dx, we're going to replace with dg over 4x minus 1. Okay. These guys cancel and give me a 2 up here. This is going to be 2 times the integral of g to the 4th dg, which is 2 times g to the 5th over 5 plus a constant, which in terms of x is 2/5 of 2x squared minus x plus 1 to the 5th and a constant. Okay. The other way you could have done this is you could have multiplied this whole thing out. You could multiply that out 4 times, then multiply it by this, and you just have a really long polynomial that you could actually take the derivative, antiderivative of, but that's a long way to do it. This is the shorter way to do it. Yeah. Okay. Let's see some other ones. I think in 5.5, they give you pretty simple ones. Let's see if I can find anything that's a little trickier. Fun. Straightforward, straightforward, straightforward. And some of them tell you which substitutions to make. So if it tells you which substitution to make, I'm not going to worry too much. So, like, for instance, this one says, and then it tells you that u equals 1 plus the square root of x. It tells you to make that substitution. Okay. I use g's because I use g's for my inside functions on chain rule. So I think if I'm going to undo the chain rule, I should use the same variable. The book uses u's for their substitutions. So we're going to get du is equal to 1/2 times x to the minus 1/2 then dx. There's an x to the minus 1/2 dx, so I'm going to get 2 du equals dx over the square root of x. And then I've got my substitution right away. This is the integral of u to the 1/3 times, well, this is equal to 2 du, so times 2 du. Then I can use just the power rule there. So u to the 4/3 divided by 4/3 times 2 plus a constant. And that ends up being 1 plus the square root of x to the 4/3. And then I've got some constant stuff that I have to figure out, 3/2. Flip it over, the 3's up top, the 2 and the 4 cancel to be just a 2 in the denominator, and then I got a plus 2. Okay. Questions on that one? That one's a little trickier, and I didn't use multiple colors. Yeah. So when you flip it up, 2 times 3/2 ends up, sorry, 2 times 3/4 ends up being 3/2. Yeah. Let's look at another one here. Oh, so when we use the chain rule on linear stuff, we always had to multiply by the slope of the linear function. You kind of remember that one? Like if I had the derivative of the sine of 5x plus 3, well, this is the cosine of 5x plus 3 times 5 because 5 was the slope. Okay. So if you have the inside function is just linear, when you're undoing that, you're just going to divide by the slope instead of multiply by the slope. So let's say I'm trying to take the integral sine of 5x plus 3 dx. Well, the antiderivative of the sine is the minus cosine, 5x plus 3. And then I have to divide by 5 because of the chain rule bit plus the constant. But if your inside thing's just linear, for the chain rule, you multiply by the 5, the slope. For the substitution, you divide by the slope. So linear functions being your inside function make things kind of nice and easy. because linear functions have a constant derivative, which turns out to make stuff nice when you have constant derivatives. Let's look at that one's straightforward. That one's straightforward. Yeah. So here's the cosine function, right? And it's decreasing. And the sine function looks like this, right? And at the start, it has positive area. So if I'm thinking about integrating from here to some value, as I go farther along, I should be increasing the area here, right? So my antiderivative should be an increasing function. So what I need to do, I know that it's related to the cosine for sure. The cosine is a decreasing function though, so I have to flip it over to make it an increasing function. At least that's how I think about it. Somebody showed me this one time. I don't know if I have it right, but cosine sine, cosine. No, let's do it this way. I think this is how it works. Cosines, so think of this on the coordinate plane. Positive x-axis is cosine positive because cosine's x and so on. Okay. And the derivative of the cosine is the sine. Sorry, the derivative of the cosine is the minus sine. So differentiation takes you this way around this circle. Derivative of the cosine is the minus sine. The derivative of the minus sine is the minus cosine. The derivative of the minus cosine is the sine. The derivative of the sine is the cosine. So differentiation takes you that way around the circle. Integration takes you this way around the circle because it undoes it. That's one way to think about it. It's not really a good way to, like, reasoning wise, a way to think about it, but maybe it's a good memory tool to figure out the differentiation and the integration, how they relate with sines and cosines. So d dx goes this way and this way and this way and this way. And integration goes this way, this way, this way, this way. Okay, let's try this one again. Get back to this one. What looks like the inside function here? X minus 10? Yeah. Yeah, 5x plus 3. Yeah, that's definitely the inside function. We ended up with the linear bit. Here I was thinking the inside function should be like x minus 10. Okay. But the derivative of x minus 10 is just 1. So what am I going to do with that x? It doesn't look like maybe that should belong there, but let's work through this. So I got x minus 10 to the 7th dx. So you might initially think that if I set g of x equal to x minus 10, and I'm just going to call it g instead of g of x anymore, g equal to x minus 10, then dg equals just dx. And so my substitution ends up being, I've still got this x sticking around. I've got g to the 7th and I've got dg. What do I do with this x? Well, this expression tells me that x is equal to g plus 10. Good with that? So I'm going to replace x with g plus 10 in here. And now this multiplication, instead of multiplying out this thing 7 times and expanding it, getting a really large polynomial, now I just have a binomial. This is integral g to the 8th plus 10 g to the 7th dg, which is g to the 9th over 9 plus 10 eighths g to the 8 plus c. And I get that. Does that make sense? Okay. So in your substitutions, you get two expressions here, your initial substitution, and then you get the derivative of that substitution. You can manipulate either one of them before you plug stuff back in, okay? A lot of times in high school, I remember the only one that I saw ever manipulated was the derivative one. But you can manipulate the initial substitution too. Both of those equations are completely valid to work with when you're doing your substitution stuff. Let's try another one. Let's try the integral of 5 over 9 plus 4 r squared dr. Okay, I'm going to pull some constant stuff out just to simplify things a little bit. So I'm going to pull 5/9 out. Pulling a 5 off the top leaves me with dr on top. Pulling a 9 off the bottom leaves me with a 1 plus 4/9 r squared. So I'm going to rewrite that as, well, let's not rewrite it yet. We'll rewrite it in a second. Looks like this. Are we okay with that? Do we know of something which, when I take the derivative, I get 1 over 1 plus something squared? Arctangent. Yeah. Derivative of the arctangent. Right? And that's kind of what this form is. So I'm going to do a u substitution where I've got this linear guy in here now. And remember what we said with linear, we just divide by the slope. Okay, so this is going to be 5/9 arctangent of 2r over 3 times, I'm going to divide by the slope. So instead of multiplying by 2/3, I'm going to multiply by 3/2. So it's going to be 5/6 arctangent of 2r over 3 plus a constant. And really my substitution is that substitution right there after I've pulled off all of that other stuff. If you can't recognize that this is the arctangent, I want to show you another way to do that. Okay. I do recognize that this looks like 1 squared plus, well, let's look at it over here. I'm still going to pull off the 5, so I've got 5/9 plus 4r squared dr. Still going to pull off the 5 because I don't want to deal with the 5. But then I'm going to have a 1. I'm going to have 3 squared plus 2r squared dr. And maybe it's easy to recognize that those two things are squares. Even if they're not squares, I could have turned them into squares. Like if I had the 5 here, I could have put the square root of 5 squared. But why I want to do it that way is because this looks like a Pythagorean theorem. And so I can draw a triangle where this side squared, if I make this the square root of 9 plus 4r squared, this side could be 3 and this side could be 2r. Are we okay with that? Okay. I'd still need another variable in here for my substitution. And so I'm going to put a theta in here. And what I end up with is I've got a constant divided by the hypotenuse squared, right? So I've got something that looks like this side over this side squared. Are we okay with that? And that's the sine. So I know that the sine of theta is equal to sine squared of theta is equal to 9 over 9 plus 4r squared. And so I can find that in here, right? If I just want the 1 over, I'll put the 9 down there, and then I can get that substitution. So I have 5 times the integral of sine squared theta over 9 dr so far. I have dr's, but I want things in terms of theta. So how do I get r in terms of theta? Well, I could use this expression and get dr, but there's an easier way to get r by itself over here. And that's this ratio. The adjacent over the hypotenuse would give me 2r over 3 is equal to the cotangent of theta. And then I get 2/3 dr is equal to the minus cosecant squared theta, d theta. We okay with that? Okay. So it's all about this triangle again. You draw the right triangle, and like I said, you can manipulate any of the substitution stuff. Well, the substitution stuff is all encapsulated in this triangle, right? I can pull this equation out of the triangle. I can pull this equation out of the triangle. I can differentiate this one to get the dr d theta out of the triangle and that sort of thing. So it's all about drawing the right triangle here. And so dr by itself is going to be a minus 2/3 times the cosecant squared of theta d theta. So here I've got 5. I'm going to pull that 9 outside. I've got sine squared theta. And then we have dr, which is going to be minus 3/2 cosecant squared theta d theta. Okay. Sine squared and cosecant squared cancel. So this is equal to minus 15 over 18 d theta. Integral. Everything is outside. One just d theta is on the inside. So that's equal to minus, well, I can divide everything by 3/5 times theta, d theta. Good with that? How do I get theta by itself? Well, I use this expression, and theta is equal to the arc cotangent of 2r over 3. We good with that? Okay, so this is equal to minus 5/6 cotangent inverse of 2r over 3 plus a constant. Well, we had that it was the positive, it was positive 5/6 arctangent. Well, arctangent and negative cotangent differ by a minus sign and a constant, right? Yeah. And so this is the exact same expression we had before. If you would have relabeled if you switched these sides of the triangle, you'd be working with the sign. You'd end up with the tangent instead of the cotangent. But that's called a trig substitution, and they're really useful. We don't get to see them until later in chapter 6, but they're still just a basic substitution. Your substitution's drawn in the picture rather than just writing down the inside function and manipulating that. You write down the picture and then you manipulate that picture. Okay, that's it for today. We'll do more substitution stuff tomorrow. You should be able to get started on 5.5 and probably 5.6 too, because 5.6 just applies the stuff from 5.5 to find areas. It combines the area stuff and the substitution stuff. So questions on 5.5 or 5.6 if you get ambitious tomorrow. I'll see you guys then.